Remember, okay, how do we study for it and what to expect? One, you will expect a lot of questions related to data analysis, yeah, which means you will be given some values to find the average and the RMS. You will be given also a lot of conceptual questions. For example, for the projectile motion, let's say if we double the initial velocity, what happens to the range, and so on. So conceptual, which is qualitative approach and not calculations like a quantitative approach like in the course. So a lot of conceptual questions related to the chapters we did, and a lot of data analysis to find the slope, to do propagation of error. And I need to tell you a secret that usually instructors are not aware of, myself. Sometimes you don't have to calculate the average. When you look at the multiple choice answers, you can pick the wrong answers and guess the right answer without doing the full calculation, especially if you are given answers that do not make sense, answers that are not well-rounded or with wrong units, you see? Yes, Mia, you will do everything data analysis. However, we are not planning to give you error on the slope unless it's something you can guess without calculation. Because I'm gonna say that, you see, I'm not well focused. I'm still thinking about the vaccine. So let me say it again. Since you are using responders, you cannot use Excel. And therefore, I don't want you to waste time doing the error on the slope on a paper. You see, you need at least an Excel spreadsheet, you know, yeah, or the line list function for you to do the error on the slope quickly. So saying that, you do not expect something time consuming, but you need to know how to find the slope using a calculator. You need to know how to find the RMS. You need to know how to find the propagation of error. You need to know how to find the error on a regular measuring tool. I would give you a measuring tool, ask you about the measurement and the error on it, which is very similar to your assignment 0. Assignment 0 meaning data analysis, the first week we had, yes. Okay, how do we study for the midterm? I wish you don't study for the midterm, because so far I believe you've been practicing all those skills, and if you did the lab reports alone and you give it a lot of thought, those lab reports, I think you can do well. You just have to review data analysis quickly and chapter 1, 2, 3, and 5, right? I don't have no idea about the grade, Gael. It's really personal. It's up to you. Probably you will struggle with time management, probably not. I cannot expect what you will end up doing. Just you should know your gaps. I think by now you know your gaps. I know that I did not give you all the lab reports. You should have lab 3 by today and lab 4 by around Thursday or Friday. I think Friday, not Thursday, because I have a deadline on Thursday. I will also send you a feedback in which I will write what is expected from you, a checklist of what you need to know, the mistakes that the students usually do. Backtracking, I think, yes, so you can go back to any question you want. However, it's not confirmed because I still need to discuss that with my other colleague, but I would fight for backtracking, because why not? Okay, you already have respondents, and the point is not to torture you, you know. Yes. What else? So that's it for the midterms. We are failing our exams because of no backtracking. I think backtracking is usually given to students to avoid cheating. That's the only purpose. And personally, as a student, if I'm ever a student, I need to go back to my questions. Like, it's better for me to manage my time. So I totally feel you. Do we have WebEx? But we have WebEx. What do you mean by WebEx? Like for us to proctor you on WebEx?
Yes, like they put no backtracking, but we're not cheating. We have WebEx, we have responders. They see us working, so we're not cheating. So I don't know why they put no backtracking.
If you're cheating or not,
even if there's backtracking.
I know. If you're cheating or not, this is... Nobody can answer this question, not even God, if God existed. Nobody can answer this question. For the students who want to cheat, they would cheat with whatever, and I believe in this. Okay? However, I know for a fact that... All right, so I don't want to talk about it. Let's do our best.
Doctor, I just have a question.
Concerning WebEx, yes, I want you to be on WebEx for two important reasons. Other than the proctoring reason, I want to be available live if you have any issue. Okay, so I will be on WebEx, I will be on WhatsApp, and I will be on email for emergency. But yes, you are required to go on WebEx with your cameras on. By the way, how do you believe this would work with Respondus? Can I see on the camera if you have Respondus on?
The doctor, we use a secondary device.
Yeah, usually we use two devices, one for Respondus and one for WebEx.
Yeah, you have no choice, I assume.
Yeah.
But that's ridiculous, probably. Okay. Yes, anyway, I'm going to send you all those in a checklist, how to get ready a day or two before the exam, okay? I'm talking about the dynamics of the exam, not the important stuff like feedback, okay? If you have any question until then, please feel free to send it to me, okay? Yeah, shall we move on to another slot in our plan? So the other thing I want us to discuss is lab number 4. Did you start with lab number 4? Do you have questions? Are you okay with it? We're okay. Anyway, if you have any question and if you remember anything, let me know. I know lab 4 is not difficult and we covered most of it very well during the presentation. We even covered all the questions like egg drop and airbag and so on. I think you're gonna be okay. Now, please make sure you always check the comments on the graded lab reports because some of you, but like I'm talking about only 10% of the students are doing the same mistakes. All right, and if you believe you already submitted a lab and you know there is a mistake there, please feel free to submit again, even if you're way beyond the deadline. It's okay. Those are assignments, they're not quizzes. The deadline is only to give you a structure, but you can submit again anytime. Let's say you remember that you did something wrong in lab number 3 and lab number 3 was due like a month ago and it's not graded yet. So how about you go and submit again? It's okay. All right, fine. So every time you read a comment and you believe you have a mistake that is done in a lab that is already submitted, go fix it, submit again. Now we're ready for lab number 6. Yes? Rotational inertia of disc and rig. I know for a fact that you started rotation in a shy way in the course, like you just started, but you know a lot from grade 11, but probably you forgot most of it. So the outline I need to follow is the following. It's gonna be rotation versus translation in general. And I love this. And I want you to see motion in terms of two and see that they are similar in many ways. Then I'm gonna discuss the moment of inertia of a point system. So I meant by here the moment of inertia of a point system. Then the moment of inertia of any system that is not point-like. It could be a rod or two point systems or a cylinder or a disc. And then I'm going to discuss the experimental setup because we're going to take a disc and a ring that is very similar to a big bracelet and create a rotation and study the moment of inertia of it. I'm going to show you how the acceleration is going to give me the moment of inertia, show you the video and the lab report. Okay? I need to tell you the lab report is not difficult. The physics behind the experiment could be confusing, exactly like rotation when we did the centripetal force. But if you get it, eventually you don't need to put in a lot of brains in it, you see? I will explain. I love this chart, translation versus rotation. I know for a fact that you understand translation very well. You know that mass is what makes you heavy, is what delays your motion in translation. Position X, velocity along the X-axis, acceleration and force, okay? On the other hand, when we talk about rotation, instead of position, we deal with angular position. So instead of meters, we have radians. Instead of meter per second, we have rad per second, all right? So this is following the X-axis and this is following a rotational axis, all right? Instead of talking about meter per second, we talk about, meter per second squared, we talk about rad per second squared. Now force, instead of talking force in newtons, we talk about torque, which is a Newton meter. And by the way, torque does not have it's not a vector quantity, it's a scalar quantity. And I do not agree with the picture. So a torque is how much the effect of the force is on rotation. So it's related to force and it's related to the lever arm, which is how far away the force is from the center of rotation. And I will discuss this again later on. Mass is inertia for translation. It makes you heavy, it will resist the motion, and so on. For rotation, I'm not going to discuss the mass. I will discuss the moment of inertia, which has a unit of kilogram dot meter squared. So it's related to the mass and it's related to how far away you are from the center of rotation. And this reminds me the famous example of the dancer on the ice skating arena, when the dancer closes his arms and start rotating so fast, you know, whenever he opens his arms, eventually he's gonna slow down because the moment of inertia increases. So it's the way you distribute the mass over the system around the center of rotation that matters, and not the mass alone. So what makes you heavy for rotation is not only the mass, it's also how the mass is distributed around the system. All right. Yes, so let me show you another table of what you want to call it, comparison probably. Instead of talking about position x, we talk about theta, angular position. This is delta x for displacement. This is delta theta for angular displacement. Velocity, we have angular velocity. Acceleration, angular acceleration. Mass, we have inertia. Force, we have torque. And please remove this vector only. And we can discuss where, by the way, kinetic energy for translation, we have one for rotation also. Instead of mass, you have I, moment of inertia. Instead of V, velocity, you have angular velocity. And you have Newton's second law as well. What is Newton's second law again? Newton's second law. Exactly, F equals ma. What do you think Newton's second law for rotation would be? And that's a vector equation. Let me stress on that. So instead of F, I'm going to use torque. Sigma F will add all torque together. Instead of M, I'm going to use the moment of inertia. Instead of A, I'm going to use alpha, the angular acceleration, which is rad per second squared. This is not a vector equation, and this is the beauty of it. However, it is a scalar, but it's algebraic. Like alpha can be clockwise or counterclockwise. The torque can be clockwise or counterclockwise, and therefore you can add or subtract depending on the direction. Yes, so probably this is what they meant by vector, and I'm gonna discuss those closely in a moment. Okay? Now, question number one, how do we calculate I? So this is our first concern before starting with the setup. How do we calculate I? You have a point, so I'm gonna take a point system. This is a point-like system, and this is the distance away from the center of rotation. This is the mass. To find I, I'm gonna take this mass times the distance away squared. So you need to know where the rotational axis is for you to find the distance away from the axis of rotation. The question for Giscard, right? Yes, the question for you is, what is the SI unit for M?
Kilograms.
Kilograms. And the unit for R?
Meters. Meters squared down.
Exactly. Squared. And I will end up to be kilogram.
Kilograms, meters squared.
Yes. Do you dance well, Giscard?
No.
Oh, yeah. I'm just trying to imagine your moment of inertia as you turn. All right, now I need to ask you a question. If I have 2-point-like system and I need to find the total moment of inertia, what do I do?
We do the summation.
Exactly. So since this is a scalar quantity, yes, you can simply add the moment of inertia. Yes, I think I need to, yeah. All right, so, and it's actually explained here. What happens if I have any system? Let's say I have a mass M, I do M times R squared. What happens if I have M1 and M2 and M3 and M4? I can simply do sigma mi r squared, like m1 r1 squared plus m2, and I can add it throughout my whole system. I mean by my whole system, it's a continuous system that is full. How do you do addition over a full system? Probably I can ask Roy. Probably Roy is in a different section. We have Gael. Yes. Gael, are you there? Thank you, Giscard. Clara, Yara, anyone? Mia? George? Am I disconnected?
Doctor.
Okay. So yes, who's speaking to me? I did not ask the questions yet. The question yet. So can I talk to George? Go ahead, George. You answer it. So my question is, George, for you. Let's say I need to add all the moment of inertia for the different masses, but I'm gonna take all this green system. How do I do the addition? Like it's an infinite number of points. How do you do the addition? Do you have an idea? Imagine I need to add all the points. What do you call sum? Do you have an idea?
It means we do the sigma of...
Yes, so I need to take every single mass.
I'm not sure.
Yeah, so basically we're gonna take the integral. The integral is the sum whenever I take all the tiny increment in mass. And it's okay if you don't know, I'm just checking if you guys know. So this is an example, and let me try to zoom in and to scroll. Just a second, because this takes time. I'm gonna remove the chat so you can see it. So basically, this is a rod. This rod is a continuous system made of an infinite number of masses. I will take a tiny piece and do m times r squared for this one, and then do the integral over the whole mass from 0 to big M, all right? So this is how we find the moment of inertia of a continuous system made of an infinite number of different masses. However, you are not required to do the integral, definitely. What you can do is the following. You can simply use this table. And this table would give you the moment of inertia in case you have a cylinder rotating around the axis of rotation, or the cylinder rotated around a different axis. This is a hoop where the axis is around the center, and this is a hoop where the axis is around the diameter. And you can see you have different moment of inertia. Okay, in our case, we're gonna take neither of those. Let me check the other table. We're gonna take this case where I have a hollow cylinder that has an outer diameter and an inner diameter. It's hollow from the inside. And we're gonna take a disc like this one. Just imagine your lunch plate. Probably take this one, yes. So it's a cylinder, it's a disc rotating around this axis. So we're gonna take this example. So this is the disc and this is the ring, okay? So instead of using the equation that is general to one point, we're gonna use the equation that is for the actual system. How did I find this equation? I did the integral over all the tiny masses in the system and found out this one, okay? I think in the course, you will be required to do the integrals, but not in the lab. You just need to know they exist. Do I make sense? Yes? All right. All right. Now, the experimental setup. What do we have? This is the ring that we're dealing with. I'm going to show you in a video in a moment. And this is the ring. The ring is empty from the inside, like it's a cylinder empty from the inside. And all this system made of both will be on a stand. So this is simply a base or a stand. However, under this, you have 3-step pulleys. I'm gonna pick only one and rotate a wire around it, like rotate the wire connected to a hanging mass. Whenever I release this hanging weight, it's gonna go down to the floor. It cannot do free fall because there's a heavy system that the hanging weight is carrying, but it's gonna pull on the wire in a way. And by pulling on a wire, it's gonna induce rotation of your platform. Not the platform, but definitely the disc and the ring. I will explain more how the wire is gonna be coiled around the pulley and how the pulling force is gonna happen, and eventually how motion is gonna happen. Okay, this is a different picture. It shows you the disc. Okay, it shows you the ring. This is the ring. It shows you the system. It says 3-stage spool. It's basically 3 wheels. You pick one. The only difference is the diameter. I assume the bigger one will create a bigger torque, even if the force is the same. And in the video, I used the bigger one. You can easily calculate the tension in the wire by doing Newton's second law for the hanging mass. This is a smart pulley. How does a smart pulley function? It's very interesting. I'm gonna show you in the video. Anyway, the smart pulley is the one that is gonna give me the speed of the hanging weight. The only way for me to study the speed of the hanging weight is to use a sensor, right? And I can use a motion sensor for that, but in this case, a smart pulley would help. A smart pulley can tell me how fast the pulley is moving, and therefore the smart pulley can give me a VT graph. The VT graph is gonna be linear because it's very similar to free fall. However, it's not so free. Okay, it's not so free. You guys, I need a second. Just give me a second. All right, so let me say it again. The smart pulley will show you that it's a linear motion V versus T. It's very similar to free fall. It's not so free though, because it's carrying a big load, you know. So the acceleration, which is the slope in a VT graph, will eventually be your objective and your target. Okay? Now I think I'm ready to start showing you how the acceleration will give you the moment of inertia of your system. Okay, it's gonna be a bit tough. The point is to know, to understand the derivations, but you are not required to do the derivations yourself. You need to understand the derivation and you need to know the final product. This would be the equation that you will use for your lab report. Okay, I'm gonna start slowly. This is the theoretical moment of inertia of the ring. I already showed you this one, right? It's the same one. So this is the equation you can use to find the theoretical value of the moment of inertia. Okay? And this equation will be used to find the theoretical moment of the disk. All right, so it's related to the mass. You can measure the mass of the disk. It's heavy though, around 2 kilograms, and R is the radius of the disk. I know that the disk given to you is not homogeneous. It has a tiny slot to put the ring on, and this could be a source of error because I'm assuming it's a full disk. All right, I'm gonna start by saying sigma F equals MA for translation, which is similar for rotation of saying that torque is moment of inertia times the angular acceleration. Okay, so I will be torque divided by the angular acceleration. Okay, now my job is to find the equation for torque, plug it in here, the equation for alpha, plug it in here, so I can have a different way to find I of my system. So this is how I find I of my system theoretically. This is I of my second system theoretically, and this is how I'm planning to find I experimentally by measuring tau or calculating tau from a measured value and measuring alpha or calculating alpha from a measured value. Okay? How do I start finding tau? Tau, by definition, if you go back to grade 11, it is the force. It's a cross product. So this is a cross product between the force and the lever arm that I can call R. So these are vectors. If you don't remember what is a cross product, since you only need the magnitude, it's basically F times R times sine the angle between F and R. Let me remind you again what R is. Let's say this is your disk, and let's say this is the force applied. Okay, this is what we're doing. We have a pulley under the system, and you have a wire rotating, and you're pulling in this direction. R is basically how far away the force is from the center of rotation. So this is R. Okay, so R is gonna be the radius of the step pulley or the radius of the pulley, or whatever you want to call it, wheel that is under your system. And F is the pulling force, or you can call it the tension. And what is the angle between R and F? Anybody can answer this question? Probably Clara. What is the angle between R and F if I make sure that this is how the wire is? Yes.
It is 90.
And what is sine
degrees.
90? What is sine 90?
1.
Yes, which means I can simply remove this one. Okay, you just need to make sure while doing the experiment to make sure that the wire is aligned on the pulley in such a way that the wire is 90 degrees. And when the students used to do the experiment on campus, not everyone had 90 degrees, and it was also a mistake. I don't want to call it an error. It would be an error only if you believe you can make sure it's 90, but you cannot control it fully. Okay, so the reason why they stated that tau is like the torque is R times T, it's because the force is called T, the tension in the wire, and R, the radius of the step pulley, is the lever arm, or how far away the force is from the center of rotation. I'm going to continue on the different slide. We just said tau is R times tension. Now my job is to find the tension. I will take this system and I can ask Yara. Yes, Yara, I need your help. Yara, do you see this hanging mass? So my question is, what are the forces on the hanging mass? It's just hanging. Yes, so you have the weight mg, right? And you have the tension T. Let's do Newton. And do you think it's in equilibrium? So is the hanging weight in equilibrium? If I release it and it's going down to the floor, is it in equilibrium? So I'm releasing my hanging, yes. So if I release the hanging weight and the hanging weight is gonna fall down to the floor slowly, do you think it's in equilibrium? So it's not gonna be in equilibrium. It's gonna speed up as while going down to the floor. Remember, the hanging weight is not just hanging, it's pulling on the wire and eventually it's going down to the floor. It's gonna speed up, and remember you have the VT graph that is gonna look linear, so you can see speeding up, you can see acceleration. So back to you, Yara. Now that you are convinced or not that we have an acceleration, how is the acceleration pointing? Is it pointing down or up? It is speeding up to the floor. So how's the acceleration? Downwards. Yes, that's so true. Let's do sigma F equals ma. I'm doing simple Newton's second law to be able to find the tension in the wire. Okay, what do you replace the tension, the net force with? Is it mg minus tension or tension minus mg? I'm gonna take the acceleration to be my positive direction. So yes, it's mg minus tension to be the net force is equal to ma. So now, Yara, how do you find tension? So it's gonna be wrong. Do it again. Yes, it's mg minus ma. Okay, all right. So now we started with this one. So now you know what to replace tension with. You simply say tension is mg minus ma. This is another explanation of why tension is mg minus ma. All right, so this is the torque. The torque is R times tension, and tension is mg minus ma. So now my other step is how to find alpha. And alpha by definition is the linear acceleration divided by the radius. I don't know if you remember this, but the best way to find x from theta is to do theta times r, right? The best way to find v from the angular speed is to do angular speed times r. And the best way to find the linear acceleration, or what we call tangential acceleration, is to take the angular acceleration times r. And you can see it with the unit rad per second times meter. I mean, rad times meter is going to be meter. Rad per second times meter is going to be meter per second squared, and so on. So this is not really an equation, it's a definition on how to find the angular acceleration by simply dividing the acceleration by the radius, okay? So I know the torque, I know alpha. So yes, this is my central one. I will replace the torque here, I will replace the alpha here, and I will have this big equation, okay? I know the derivation is big, you just need to understand the steps, and please let me know if you did not understand one of the steps. Your job is to finally understand the final product. I did tau divided by alpha. This is tau, and this is alpha. And yes, there is a typo mistake. This is divided and not plus. So this is divided and not plus. Dividing by an actual fraction is multiplying by the inverse. And then you're gonna expand and you will end up with this product, mr squared. Just a second, scrolling is difficult when I'm recording the session. So this is I of your system. So I of your system, whatever your system is related to the hanging mass. That you need to understand that this is the hanging mass. This is R of the step pulley. So it depends which step pulley, and the step pulley is this wheel under the system. Yes, if you're using a bigger one, you're gonna pull more with a bigger torque and therefore create a faster rotation. G is gravity. A is the acceleration of the hanging mass that can be measured. The pulley is gonna give you A directly. So this would give you I, and you need to understand that the bigger the acceleration, the smaller the I. It means your system is not so heavy. It's not resisting the motion a lot, you see. So since you don't have a measuring tool that would give you I directly, the measuring tool will give you a VT graph. The VT graph will help you find the acceleration, which is only the slope. By finding acceleration, you do the calculation to find I. You're gonna do the experiment where you have the disc only, and then you will do the experiment again when you have the disc and the ring, because you cannot put the ring alone. So you will find I of the disc only, and then I of system, disc and the ring together, okay? So did you understand how I derived the final equation? I know it's time consuming, so probably you missed a step. I know it's not tough. I know probably you don't remember some of it. That's why it could be confusing for you. Did you understand the different steps? Any question? Just ask and don't stress, because you are not required to know the steps. But if you do understand, it's easier to understand the experiment. Questions? No questions?
Doctor, do we have any uncertainties?
You're worried about uncertainties. Yes, you need to do propagation of error. Not over this, probably over this one. Just the theoretical I and the theoretical R. I will show you the lab report in a moment to answer your question, okay?
Okay.
Any other question before I move on to the actual experiment? I'm gonna take your silence to be positive. So, or negative, like no questions. This is the disk I'm talking about. And you see the platform. This is disk and ring. So you see there's a slot where I put the ring on. And you see the slot here, like some empty hole. Okay. Here I'm trying to rotate the wire around the pulley, and you will see it in the video. This is the whole system. This is a pulley with a photo gate. I'm gonna call the whole thing a smart pulley. This is a VT graph. You see a linear function, and then this is where the wire or the hanging mass is gonna collide in the floor, collide with the floor. So I'm gonna ignore this part, okay? I will take the slope. You see the yellow selection. I select only the linear part to find the slope. Okay, now the video. Which one comes first? This one. In this video, let me make it, increase it in size. And yes, this was recorded by Ms. Jinan helping me. And this was done 2 Mondays ago. Yes, so let me show you what we have on fast forward. By the way, this is the platform. This is the pulley with the photo gate. We can call it smart pulley. You see wheel number 1, 2, 3, and we have a wire that may not be visible. I can rotate the wire along any wheel. This is called a step pulley. Any step pulley I want. If I use the bigger pulley, the torque is gonna be bigger, you know, which means less force, faster rotation. Okay, so I'm explaining, showing you the disc, explaining how heavy the disc is. I will put the disc on the platform. It has a slot. It rotates very smoothly. Okay, while rotating, by the way, you see the hanging weight. As it's rotating, the wire was rotating around the wheel meaning step pulley, and that's why the hanging weight was going up. By the way, the weight was so light. I needed to put extra weight for the system to go down. It was so light, it wouldn't pull the heavy disc down. Okay, now I'm showing you how I put the ring on top, just to understand the equipment used. I'm not doing the experiment yet. I'm just explaining that the heavier it is, the slower the rotation is. Yeah, now I'm showing you the wire, the hanging weight, how the wire should be over the pulley, and the photo gate, the smart pulley. Yes, and I'm gonna show you that you have 3 wheels, each of which has a different diameter, and how I decide to rotate the wire around the bigger diameter. Okay, please stop me and ask if you believe this is not clear. So the 90 degrees is the angle between the wire and the radius of the wheel. I made sure that the pulley is aligned with the wire. Initially, the pulley was pointing in a different direction. So I aligned it with the wire before setting the video, probably, or probably now, I don't know. So I rotated again. I'm trying to see if the rotation, you see, like here, the angle is not perfectly 90, but very close to 90. But if I simply move the pulley, turn it a bit, it's gonna be closer to 90. Okay, this is the hanging weight. It's not so heavy. It's gonna actually go down on the floor, but when I put the disc is so heavy, it has a lot of inertia. Like a tiny force will not be able to rotate it easily. It's like Giscard dancing. Yes, rotating on the platform. That's for the first video. For the second video, I'm gonna, change, yes. So I'm explaining a bit how the photo gate functions. Very interesting to understand, actually. The photo gate sends a signal, like your remote control, like an infrared signal between this terminal and this terminal. And every time I block the signal with my finger, it will register the time through the block. And you know, the pulley has some empty slots and some full slots. And every time a full slot will block the beam, the photo gate is registering how many times and for how long. That's why the photo gate can tell how fast the wheel or the pulley is, you know. Here for a second, I took some time to explain the functioning of the photo gate. You see, it has light going on and off every time I unblock the beam. Okay, you can see it here, during which it's blocking the beam. So how can I use this? I was blocking the beam simply with my finger to show you that I can block it fast or slow. This through the smart pulley. Every time the pulley is rotating, it can measure the time through which the beam has been blocked. Knowing the sizes of the black plastic beams of the pulley, it can tell the speed. So, all right, so basically this is a photo gate and it tells you how fast the linear speed of the pulley. Definitely the data studio should know the size of the pulley, the thickness of the black slots of the pulley, and so on, because the photo gate is measuring time and not speed. The speed is basically calculated through the app, right? All right, so if I continue a bit through the video, I show you the VT graph, I show you the linear part that is highlighted in yellow, and also you can see that after a certain beautiful linear behavior, you have suddenly random behavior. This random behavior is whenever the wire is done, it's over, or probably the hanging weight just hits the floor. And sometimes it does if the wire is long enough. So I continue explaining what happened and basically the slope given. You cannot read the slope on the video because it's not, the resolution is bad, but it will be given to you later on. Now I'm gonna do the actual experiment. I will rotate the wire on the big wheel. I'm rotating it right now, making sure the wire is beautifully rotated. I delete the graph, I erase it, and I release my system. It's gonna rotate slowly, let's see. Very, very slow. It could be that the hanging weight is actually very, very small. I will repeat the experiment with a bigger hanging weight, but let me see, probably this would be good enough. I can see some acceleration, but it's still very small. All right, if you compare the acceleration of the hanging weight to free fall acceleration, you will see that the acceleration is very small, like below 1 meter per second squared. Free fall acceleration is how much, George? Yes, George. Free fall acceleration is how much? Clara? Yes, George. Okay. So free fall acceleration is 9.8 meter per second squared. You will deal with values sometimes smaller than 1, depending on how, I'm checking if it's related. Yeah, it's basically, I don't know actually. You're going to see it in the results. It's going to be very small compared to 9.8. This would tell you how big the inertia of the disk is. By the way, do you see that the slope here is very, very small? You can barely see the graph. I had to zoom in to find and to select only the linear part. Let me show you again that here I was zooming in, selecting only the linear part. Initially, I selected the whole thing, and then I moved the selection to the linear part only to find the slope which is written in this box as M. All right, now here I increase the hanging mass. It shouldn't depend on the hanging mass. The acceleration will, but not I. So I'm gonna repeat the experiment, and you will see again a linear behavior that is more visible because the acceleration is a bit greater. And I'm gonna select only the part that is linear and find the slope. Okay, now let me show you the lab report because it's really simple. What you need to do, first of all, you need to fill in this table. These are pre-known values. The step pulley radius, which step pulley or wheel did I use? I'm gonna give you the value. I used it using a regular ruler. I measured it using a regular ruler, so you know what uncertainty you have. The measurement of the inner radius and outer radius of the ring is also measured with a regular ruler. The radius of the disc, a regular ruler. The mass of the ring, digital measuring tool. Mass of the ring and disc, both same measuring tool, digital. And I'm gonna write it down for you. The hanging mass is also same measuring tool, digital. You will be given the values and I will tell you which measuring tools I used. Now you need to calculate the theoretical values for I-disc and I-ring, and you know for a fact that you have those to use. Theoretical equation for the ring, theoretical equation for the disc. And you have to find the uncertainty using propagation of error. So far, so good? I will repeat 10 trials when I have ring and disc together. The slope using Data Studio. By the way, each repetition will take me less than a minute, so it's really fast. Do the disc alone. Find the average and the RMS value for A. Then use this equation from A, find I. And I can find I in general, which is I of the disc experimental. Knowing I of the disc experimental, I can compare it with I of the disc theoretical. Now the question for Clara is, how do I find I of the ring experimentally? I cannot put the ring on my platform alone. Usually I put it with the disc. So experimentally, I can find I of disc plus ring. How would you find I of ring alone experimentally, Clara? So how can I find experimentally I of the ring? I cannot put the ring alone on the platform. It does not have a slot to go on the platform. I can only put it on the disk. Do you have an idea, Clara? No? Okay. Probably I can ask Josepina. I did not talk to you today. Do you have an idea how to find I of the ring? I have the acceleration for the ring. And for the ring and the disk together. And this would give me I for the disk and the ring together. How do I find I of the ring alone? Do you have an idea, Josepina?
Doctor,
Yes, I couldn't hear you.
I don't know.
All right. Mia, do you know how? Mia, do you want me to repeat the question? Yes, Mia, I'm all ears. Okay, what about Rita? Do you know how?
Do we have a formula can be relating I and A?
Yes. So
we use the A تبع ring and we calculate the I.
Okay, so we have A. Let me show you here. We have A for ring and disk together. So this would give me I of the ring and disk together. And we have A for the disk alone. And this will give me I of the disk alone. Now, how do I find I of the ring only? You're very close.
We substitute.
Yes, what do you mean by substitute?
Minus. يعني.
Yes, thank you, Zilla, and thank you, Rita. And yes, George, they're additive, so we minus. So for the students who did not understand or do not know the answer, by knowing I of the disk, knowing I of disk plus ring together, you could simply minus the I of the disk from it. Remember, I is the moment of inertia. It's very similar to the mass. If I measure my mass along with my laptop, to know the mass of the laptop, I can simply do minus my mass. Very simple. And yes, you can do that with the moment of inertia. Okay, so basically that's all you have to do. Let me recap. What you need to know is the smart pulley will give you the acceleration of your system. From the acceleration, you can find I that I'm going to call experimental I. Knowing the theoretical I and the experimental I, you can compare, okay? The idea of rotation by itself could be confusing for some students. I by itself could be confusing because you don't deal a lot without I throughout your school years. So you know a lot about mass, but not I. Think about I being how heavy an object is. Heaviness for rotation is not only the mass, it's the mass and how it is distributed along the axis of rotation. Okay, just imagine Giscard doing the dance and you will never ever forget what I is. Okay, so any questions? Yes, that's it. I'm gonna save as the edited PowerPoint to send it to you. Yes, I will stop recording as well. Giscard, what's wrong? You're dancing because you're happy.